Jai Hind to all. Today I am here to present the lecture on subject D, Digital Signal Processing KC 503, and the first lecture is realization of ladder structures. I am Dr. Amit Garg, Associate Professor in EC Department of Ajay Kumar Garg Engineering College. Okay, let us start with the realization of ladder structures. So, before starting this ladder structure realization, I'll discuss IR filter realization. Some points like in IR filter realization, you will see there are so many methods. Okay, so if you will see in IR filter realization, so many methods like direct form 1, direct form 2, cascade, parallel. So all these are realization techniques. Another one is your ladder that we are going to study. Okay, so if we'll see the issue with these type of structures like direct form 1, direct form 2, cascade or parallel is that when we are designing, when we are realizing these structures, so in all these structures there is some issue like coefficients are sensitive to change in the parameter values, so that the frequency response of the system gets changed and your system will become unstable. So that is the issue with these type of structures. So that's why these ladder structures came into existence. So if you'll see the ladder structure, now come to the ladder structure, and filters realize using ladder structures have desirable coefficient sensitivity properties. Small changes in the filter parameters have little effect on its performance. Okay, so that's why we are using these ladder structures. We found these ladder structures more useful as compared to these above structures. Okay, because in ladder structures, the coefficients of ladder structures have desirable coefficient sensitivity property. Means these are less affected by change in parameter variations. And we can see if we will do some small changes in the filter parameters, it will have little effect on its performance. Means what happened, if we will see the coefficient of filter, then those coefficient of filters are less sensitive to change. Okay, so if those coefficients are less sensitive to change, then there are less chances of this transfer function get changed. And with this transfer function will not change, in that case there are very less chances of changing in frequency response. And if the frequency response is okay, then our system will operate in stable region. Okay, so that's why we use these ladder structures. Okay, now we come to the realization part. So if we are having a filter transfer function which is represented in this form, then it can be represented as ladder structures. Okay, where an minus 1, a1 a naught, bn minus 1, b1 b naught, all these are you can say the values of different powers of z in the given transfer function. Okay, so now you can see here that the maximum power of z is n and n, means you can see here the similar power is there. Okay, so for realizing this, first of all we have to split this transfer function so that we can realize the individual components of this transfer function. Okay, so for doing this, what we have to do, we have to do the continued fraction expansion of hz. Continuous fraction expansion means we will divide numerator by the denominator, we will divide numerator by the denominator, and then we will get the remainder, and then we will again divide it like so. This process will be continued. So you will see the continued fraction expansion of this transfer function will be of this type: alpha naught plus 1 upon beta 1 z to the power minus 1 plus 1 upon alpha 1 plus 1 upon beta 2 z to the power minus 1 plus 1 upon alpha n, you can say. So you are having when you are having the values of alpha naught, beta 1, alpha 1, beta 2 and alpha n, then you are having the transfer function hz in continued fraction expansion form. Okay, so what we have to do, these are filter parameters, these are nothing but filter parameters. So we have to calculate these parameters alpha naught, beta 1, alpha 1, beta 2, alpha n based on this transfer function, based on the transfer function values of an minus 1, a1, a naught, bn minus 1, b1, b naught. Okay, so this is the generalized equation, this is the generalized transfer function. So you can say we have taken this value as n. But let us suppose if our system is of third order. So if system is of third order, then you can see that has power, then the value of n will become 3. Then if the value of n will become 3, then you can see this equation will be a cube z to the power minus 3 plus a2 z to the power minus 2. Like this you are having the equation in specific form. Okay. So now important aspect is that how we can calculate these coefficients value alpha naught, beta 1, alpha 1, beta 2 and up to so on alpha n. So alpha n is, let's say order is 3, then this alpha n will become alpha 3. So your continued fraction expansion form will be for n equals to 3 alpha naught plus 1 upon beta 1 z to the power minus 1 plus 1 upon alpha 1 plus 1 upon beta 2 z to the power minus 1 plus 1 upon alpha 3. So these are the coefficient values that we have to calculate. Okay. So now important aspect is that how we will calculate these coefficient values alpha naught, beta 1, alpha 1, beta 2 and up to so on alpha n. How we will calculate these coefficient values? So these coefficient values can be calculated using a method given by Routh. So Routh is a scientist who has given one method by which we can calculate the various coefficient values. These are the filter coefficients. So we can calculate this using Routh array. So Routh array, so we will see how we will make a Routh array and how we will calculate the coefficient values. Okay. So to calculate the values of alpha i's and beta i's from the Routh array, we will make a Routh array. So Routh array will consist of, you can see in generalized form, z to the power minus n, z to the power minus n, z to the power minus n plus 1, z to the power minus n plus 1, z to the power minus n plus 2 and up to so n until we will get not z to the power 0 or z to the power 0, which you have written over here as 1 1. So let us suppose if n equals to 3, then you can see over here that this value will be z to the power minus 3, z to the power minus 3, z to the power minus 2, z to the power minus 2, z to the power minus 1, z to the power minus 1 and then z to the power 0 or z to the power 0, which is 1 and 1. And now how we will make the Routh array? So we will take first, as per this we will take first row of the numerator. So you can see the coefficients are an minus 1, an minus 2 up to so n a naught. Okay. And for denominator we can see the coefficients are bn minus 1 up to so n b1 and b naught. So these are the initial two rows of Routh array that can be obtained from the given transfer function. Okay. So once you have these first two rows of Routh array, we can calculate all these coefficient values. Like if we have to calculate Cn minus 1. So Cn minus 1 can be calculated using, how we will calculate Cn minus 1? Cn minus 1 will be equal to Bn into A of n minus 1 minus an into b of n minus 1 upon bn. Okay. So by this manner we can calculate Cn minus 1. For Cn minus 2, how will calculate this value? For calculating this value, we will multiply bn into an minus 2 minus an into bn minus 2 upon Cn minus 1. So you will get this value Cn minus 2. So what you will do, you will calculate all these coefficient values. So once you will get this row, then you will calculate dn minus 1. Now what is the value of dn minus 1? So dn minus 1 will be equal to Cn minus 1 into bn minus 1 minus bn into c of n minus 2 upon c of n minus 1. So what we will do, this is generalized form. So what we will do, we will complete this Routh array like this, and then Cn, then Dn, then En, then Fn minus 2, all these values can be calculated until we are not having the 0 values correspondingly. Okay. So once we will complete, so our aim is what? So our aim is to complete the first column of Routh array, because it is used for the calculation of these coefficients. Okay. So once you will complete this Routh array, where all the elements, no element is 0 in this case, and you will calculate all these values, then you can calculate these coefficient values like alpha naught. Like if you have to calculate alpha naught, that alpha naught will be equal to an upon bn. Okay, alpha naught will be equal to an upon bn. Next coefficient will be equal to beta 1, and that will be equal to bn upon Cn minus 1. dn upon cn minus 1. Then next coefficient will become alpha 1. Alpha 1 is next coefficient will become alpha 1. Alpha 1 is cn minus 1 upon dn minus 1. Similarly, next coefficient is beta 2. Beta 2 is dn minus 1 upon en minus 2. Like this, we will calculate, like if you calculate alpha beta 2, then beta 2 will be equal to dn minus 1 upon en minus 1. Like this, you will calculate en minus 2. So like this, you will calculate all the coefficient values. Like if you have to calculate alpha 2, then alpha 2 will become en minus 2 upon, if you will see here, this is f of n minus 2. So like this, you will calculate all these coefficient values. Okay. So if this type of question is given to you and you have to find out the ladder structure realization, then there are two parts for solving this particular problem. First part is to obtain the continued fraction expansion of this transfer function which is given to you. Then that you will calculate like this. So first part is over, means you have calculated all these coefficient values and you will put these values over here. So you will get hz in continued fraction expansion form. Okay. So first part is this. Now second part is this. Once you have obtained the transfer function hz in required form, then you can realize this using a structure, and that structure you know is composed of basically like multipliers, adders and del elements. Okay, multipliers, adders and del elements. So this is your del element, this is your multiplier and these are the adders. So we will realize this structure using the multipliers, adders and del elements. Okay. Now second part is, first part we have obtained the continued fraction expansion, means hz in continued fraction expansion form. Now once we have this continued fraction expansion form of hz with us, now we will realize this structure. Now we will see what general type of structure we will obtain. Okay. So you can see this system can be represented by yz equals to hz into xz, where hz is the system function. So what we can do basically, this hz you can see here, this hz we are using its continued fraction expansion form. So what we are doing, alpha naught plus 1 upon beta 1 z to the power minus 1, and this whole term we are taking as let's say r1z. Okay, so this hz can be written like alpha naught plus 1 upon beta 1 z to the power minus 1 plus 1 upon r1 z, like this. So this is the system function and we are multiplying it by xz. So then we will realize it. So we will get alpha naught xz plus this term multiplied by xz. So we are assuming that this term h1z is nothing but 1 upon beta 1 z to the power minus 1 plus 1 upon r1z, which is written over here. Okay. Now if we have to realize equation 1, so you can see there is plus sign in between these two values. So what we have to do basically, we have to take its parallel realization, because we have to add up two subsystems. Okay. So yz will be equal to alpha naught xz is one subsystem and h1z xz is another subsystem. Okay. So how can we represent it like this? This is alpha naught. So how can we represent it like this? So this is alpha naught xz plus h1z times xz, and let us suppose the output of this subsystem is y1z. So the output xz into multiply by h1z, that will become y1z. So we will obtain y1z over here, which we can use later on. So your xz will be equal to alpha naught, sorry, yz equals to alpha naught xz plus xz into h1z, that will be called, that will be become y1z. So this is the realization of equation 1. Okay. Now what we will do, now we will split this r1z, Now you can see, according to this equation, this r1z can be further written like this. r1z will be equal to alpha 1 plus 1 upon, you can see over here, this whole term is r1z. So now r1z we are writing like alpha 1, this term, plus 1 upon beta 2 z to the power minus 1, this term we have taken. Now the rest of the whole part we are assuming it as r2z, means this is the another subsystem. Okay. So this is basically how we will split r1z. r1z when we are splitting, then we are assuming that the rest of the transfer function is r2z. Okay, so we are assuming later on, like we will see later on this thing. So you are having R1Z in this form. This we are saying that this is equation number A. So now we want to realize this equation number A. So first step in realization of equation A is if we realize equation 1 in parallel form. Equation 1 is this, and we have to realize it in parallel form, where y1z is the output of subsystem having h1z as system function. So if we will realize equation number 1, so this is the realization of equation number which can be used for the realization of equation number A. Okay. Now we will take this equation h1z equals to 1 upon beta 1z to the power minus 1 plus 1 upon r1z, and here you can see h1z is, this is the output and this is the input. So h1z is nothing but y1z upon xz, y1z upon xz, h1z will be equal to y1z upon xz, and this is equal to 1 upon alpha 1 upon beta 1z to the power minus 1 plus 1 upon r1z. Okay, so we will get this equation number 2. Now cross multiply. So by cross multiplying you are having y1z multiplied by beta 1z to the power minus 1 plus 1 upon r1z, and that will be equal to xz. Now for representing it in cause and effect form, we will write like we will solve it. So we will get this term y1z equals to r1z times xz minus beta 1z to the power minus 1 y1z. Okay. Now what we are assuming that again this term is, let's say, is equal to x1z. So x1z will be equal to xz minus beta 1z to the power minus 1 y1z. Okay. You can see this as equation number 4. This is your equation number 3. Okay. So we are having this equation. Now we obtain a realization of equation number 4 using equation 2 and equation 3. So now we are having 3 equations. With the help of these 3 equations, we will realize this structure. So you can see here is the input is xz and output is the y1z. From where we have got this, we are realizing this part. This part we have already realized. Now we are dividing this part so that we can realize it. Okay. So xz and input is xz and output is y1z. You can see over here. Now the structure in between is this. How we are getting this structure? Because the output is y1z here, and according to this equation, this input x1z. So where is the input x1z? x1z is this input. Okay. So how x1z is xz? So xz is here and minus beta 1z to the power minus 1 y1z. Okay. So minus beta 1 is the coefficient multiplier in the feedback path, z to the power minus 1 is there, and output is this. This output is nothing but y1z. y1z how we are getting? y1z is, if you will see, y1z will be equal to from here h1z into xz, or y1z kya hai? Or you can see here y1z will be equal to, from according to this equation, x1z into r1z. Okay. So this is the structure where input is xz and output is y1z. Okay. So this is your multiplier, this is your delay element, these are your adders. Now what we will see, what we can see now, if you will see the equation number, or you see the realization of equation number 1, you can see this h1z. h1z is having input xz and output y1z. So you can see here is the input xz and output y1z. So now what we will do, we will replace this structure, we will replace h1z by this complete structure. Okay. So when you will replace it this with complete structure, you are having your new structure like this. So now combining the structure shown in figure 1 and figure 2 to yield the structure shown in figure 3. So now the amended structure is like this, where in place of h1z, now you are having the term of r1z. Okay. So the next step in the realization of hz is to obtain a realization of r1z that can be used in figure 3 if we write the expression for r1z. Okay. So now in this similar manner, r1z can be written as this term and this term. Again we are splitting this transfer function as r1z as something into r2z form. Okay. So again your input is x1z and output is y1z. So you can see here in this structure, input is x1z and output is y1z. Okay. So how we are doing this? We are comparing like similar manner we have obtained this figure 3, we are obtaining this figure 4. Okay. So in place of alpha naught, now for this x1z and y1z we are implementing this structure, and its value is, like you can see, r1z will be equal to y1z upon x1z, and its value will become, if you will see from here, from the very first slide. So here you will get this solution. Okay. So r1z will be equal to y1z upon x1z, and it can be written as alpha 1 plus 1 upon beta to z to the power minus 1 plus r2z. So now again we are splitting this r1z term in terms of something into r2z. So we are having this alpha 1 term, we are having this beta 2 term with negative sign, and r2z. So what happened now, we will replace this r1z by this complete structure. So you are having structure like this part, and instead of this part we are having this part. But again r2z is there, which can be further, you can say further divided. So the overall realization structure is like this. Okay, like we have splitted h1z in form of r1z, we can split r1z in r2z form, and further r2z can be continued in something into r3z form, until or unless we are not covered all the coefficients. Okay, so once we cover all the coefficients, the final structure will be obtained after continued, after this process will be continued. Okay, so this is the final structure. You can see first alpha naught term will be there, then minus beta 1 term will be there in the feedback path, then alpha 1, then minus beta 2, then alpha 2 minus beta n, like this. These you can say dotted lines. So this structure will be continued and ends at alpha n. Okay, so this is the complete generalized structure. Okay, and this is ladder structure. You can see the important thing is that in feed forward path your alpha naught, alpha 1, these multipliers came, and feedback path you can see that delay elements will occur, and it is in feedback path. Okay, multiplied by a multiplier with negative sign. Okay, so now so this is the generalized theory, that how we will obtain the continued fraction expansion, how we have obtained this continued fraction expansion, and with the help of that continued fraction expansion, how we will realize a structure, that is this structure. Okay, so this is your one complete problem. Now we will see it using an example. Initially I have taken general form, but right now specifically the question is given to you like given the system function is given like this, realize this using ladder structure. Okay, realize this using ladder structure. So first of all we have to check that what is the initial value. Is write it this like 6z to the power minus 2 plus 8z to the power minus 1 plus 2 upon 12z to the power minus 2 plus 8z to the power minus 1 plus 1. Okay, now you can compare it with this standard equation a n z to the power minus n plus a n minus 1 z to the power n plus 1, like this. So you can see the coefficient values. Now you can see the coefficient values are a n z to the power minus n. So n will be equal to 2. So these coefficients will be started from a2 z to the power minus 2 plus a1 z to the power minus 1 plus 2 and 12 z to the power minus 2. Okay, so here n will become 2. So we will make a Raoult array. So here z to the power minus n, z to the power minus n means z to the power minus 2 and z to the power minus 2. Later on in third and fourth row, terms related with z to the power minus 1 will occur, and then z to the power 0 or 1 will occur. Now we will write the coefficients. So coefficients will be 6, 8 and 2, 6, 8 and 2, and here denominator coefficient 12, 8 and 1. Now how we will obtain this value? This value will be obtained if we will multiply 12 into 8 minus 6 into 8 divided by 4. So this value will become 12. Oh sorry, 12 into 8 minus 6 into 8, sorry, divided by, it is not 4, it is divided by 12. So will divided by 12. So this value will come 48 upon 12, that will become 4. So this value will become 4. Now how will obtain this value? 3 by 2, 12 into 2 minus 6 into 1 upon 12. So this will become 18 by 12. It means 3 by 2. So we will get this value. and for solving this value, there needs some term over here. If there is no term here, so all these values are 0. So you are having now 3 terms. Now this term will be obtained by 4 into 8 minus 12 into 3 by 2 upon 4. So we will get this term. 4 into 1 minus 12 into 0 upon 4. So it will get 1. Like this, we will complete this Routh array. So next term will be 5 by 14 and 1. Now you have to calculate the coefficient values. Okay. So coefficient alpha naught will be 6 by 12. That will become 1 by 2. Then next coefficient is beta 1. That will be 12 by 4. That is 3. Third coefficient is alpha 1. That is 4 upon 7 by 2. It means 8 by 7. Next coefficient value is beta 2. That is 7 by 2 upon 5 by 14. So this will become 49 by 5. And last value is 5 by 14 divided by 1. So this is 5 by 14. So now we have obtained all the coefficients. Now we will write these coefficients in continued fraction expansion form. So if you will see what is this continued fraction expansion form, hz equals to alpha naught plus 1 upon beta 1 z to the power minus 1, like this. So we will write this in this form. So hz equals to alpha naught plus 1 upon beta 1 z to the power minus 1 plus 1 upon alpha 1 plus 1 upon beta 2 z to the power minus 1 plus 1 upon alpha 2. So that is why this term is 1 upon 5 by 14, or you can write it like 14 by 5. So this is the continued fraction expansion. Now if you will solve this, structure from in this direction, means from here you will take LCM, solve it, then you will take solve it, then finally you will get this structure. But it is not a very easy task to obtain this form from this form directly by simple mathematics. So that is why we have used this Routh array technique. Okay, now we will draw the structure. So once you have obtained this hz in continued fraction expansion form, then you can directly draw this structure like this. So here is the input xz and here is the output yz. So first of all you require alpha naught. So alpha naught is 1 by 2. You can see this value is 1 by 2. Next is minus beta 1 and z to the power minus 1. So you can see minus beta 1 is 3. So here is the term minus 3 into z to the power minus 1. Okay. Later on the next term is your 8 by your alpha 1, that is 8 by 7. So you can see here alpha 1 multiplier alpha 1 is put. So you will put 8 by 7 over here. Okay. Then later on it will become beta 2. So beta 2, here you can see in the structure the value is minus beta 2. So this is minus 49 upon 5 and z to the power minus 1, and the last value is alpha 2, that will be equal to 5 by 14. Okay. So you will put alpha 2 over here. Okay. You can see here. Okay. So now important thing is that where we have to put adders, adders are always there where two signals are added. So if you are getting some output over here, so input comes over here and input comes over here. Okay. And here in this adder you can see input comes over here in this direction. Okay. So you can see your signal flow direction is from here to here and from here to here. So it is important that you have to alternately put the adders here, 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 like this. Okay. Important thing is that all the beta coefficients we have given the names coefficients as alpha naught, beta 1, beta 2, alpha 2. Why? We can give it like alpha naught, alpha 1, alpha 2, alpha 3, alpha 4. So for distinguishing, because all these beta coefficients came in the feedback path, and all the alpha naught, alpha coefficients came in feed forward path. Okay. So that's why for distinguishing we have given these coefficients like this, so that you can obtain this structure in this form. Okay. So this is first we will obtain, we will make a Routh array, then we will obtain the coefficient values. With the help of those coefficient values we will obtain this system function hz, which is given in continued fraction expansion form, and after obtaining this coefficients and continued fraction expansion form, we can draw this structure like this. Important thing is adders are alternate right left like this. Okay. So this is how we can obtain the ladder structure realization. So this structure is more robust as compared to your IIR filter realization, other techniques of IIR filter realization which I have discussed earlier, that is your direct form 1, direct form 2, cascade and parallel realization structure. Okay. So thank you very much for your kind consideration of my lecture. Okay. Thank you so much.